Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy tutorials. In this ROS2 Jazzy tutorial we explain how to parametrize robot models by using the Xacro language. Note over here that the word Xacro can also be pronounced as Xacro. However, in this video tutorial I'm going to use Xacro pronunciation. Xacro is an XML macro language that enables us to completely parametrize the robot description and write more readable and compressed robot model files. It is an extension and addition to the Unified Robot Description Format or URDF language for modeling the robot geometry and dynamics properties. The material presented in this tutorial is of the paramount importance for modeling and visualizing robot geometry and dynamics properties. And here is a brief demonstration of what you will learn in this video tutorial. Over here, you can see a model of a robot consisting of two links and a single joint. And we can move this joint by using this slider over here. And you can see that it's a single revolute or rotational joint. This model is completely parametrized by using the Xacro macro language, namely, over here, if I open the implementation file, you will see this. This is the modified URDF file description format, or to be more precise, the Xacro macro file. You can see how the links are defined, and you can see that everything is parametrized. You can see A, B, C, which are the dimensions of the links, A, B, and C dimensions. And over here you can also see additional properties. If I open this file, that is an additional file, you can see that I implemented the moments of inertia of every link and that I implemented additional parameters. And over here, if you want to change the basic parameters, you will simply go here and enter the values you want, and everything will be modified later on. In particular, in this tutorial we explain, number one, how to write a ROS2 package and a Python launch file for displaying a robot model in RViz. Number two, how to parametrize the robot geometry and dynamics description by using the Xacro macro language. And number three, how to implement mathematics formulas by using the Xacro macro language. In addition to this video tutorial, we have created this manual that explains in detail all the steps that you need to perform in order to implement the exercise explained in this video tutorial. And in addition, we have created a complete ROS2 package, including the Python launch files, including the Xacro file, CMake lists, and additional files. A link to all these files, including the manual, will be given in the description below this video tutorial. Here's the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number one, the learning material is the ownership and the original work of Dr. Alexander Haber, who is the author of this video. Number two, you have the right to use the learning material for personal educational use and strictly for non-commercial use. Number three, the learning material should not be copied, redistributed, or publicly posted on public and private websites, code repositories, and social media platforms. Number four, the learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Number five, unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Number six, unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers, including but not limited to paid students, paid postdocs, paid professors, etc. Number seven, the provided code files and the learning material should not be used to train an AI algorithm or a large language model. And number eight, unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Okay, let's start. The first step is to open a terminal. Click here and search for terminal. Then I'm going to resize this terminal window such that you can see what I'm typing and at the same time you can follow this manual. Let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics, so keep in mind that. Install Linux Ubuntu on a computer if you don't have it. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. So let's verify that you have the correct Linux Ubuntu distribution. To do that, you simply need to execute this command. This command will list your current Linux Ubuntu distribution and you should see something like this. Here you can see that I'm using Ubuntu 24.04 and this third number over here is not relevant. Okay, the next step is to verify that you have ROS2 Jazzy Jalisco installed on your system. If you don't have it, then go to the YouTube channel and search for ROS2 Jazzy Jalisco installation and you will find several tutorials. To verify that ROS2 Jazzy Jalisco is installed, we will list the content of the standard installation folder. That is, we will list the content of this folder. And if you see something like this, then most likely ROS2 Jazzy is installed on your system. However, we still need to perform the additional verification. First of all, let's try to execute this source file. This source file, or better to say the configuration file called setup.bash, will properly set up and configure your ROS2 underlay such that you can run ROS2 commands in your terminal. So let's try to do this, and if you don't see any error, then most likely ROS2 Jazzy is properly installed. However, let's try to print this environment variable, and if ROS2 Jazzy is installed, then you should see as the response Jazzy, and that should be it. And let's continue further. The next step is to install the necessary ROS2 packages or verify that they are installed. In this tutorial, we will need several ROS2 packages. Most likely these packages are already installed if you have followed the instructions for installing the full ROS2 Jazzy desktop version. However, in case you miss some ROS2 installation steps, it is still a good idea to run the package installation commands. We will need several packages. First, we will need the joint state publisher GUI, which enables us to set the joint position and orientation and to publish the joint state messages. This is a package that creates a graphics user interface or GUI for setting and publishing joint state values for a given URDF. And that's the slider from the beginning of this video tutorial. Then we will need the robot state publisher package for the robot state publisher node. We will also need the RViz package. This package is used to visualize the geometry and motion of a robot by using a simple GUI. Finally, we need the Xacro package in order to parametrize the robot model and create macros. So let's do it. First of all, I'm going to close this terminal and open a new terminal in order to engrave in your minds that you should always source the environment whenever you want to play with ROS. So first of all, run this command. Then run these two commands, sudo apt update and sudo apt upgrade. This will update and upgrade all the packages on your system, and consequently over here be patient until this command is executed, and press Y over here. The next step is to install the necessary packages. Let's first install the joint state publisher graphics user interface. Most likely you have them on your system. Then let's install the robot state publisher. Then let's install the RViz. And then let's install the Xacro package, such that we can use the Xacro language. The next thing to learn is how to list all the packages. To list all the ROS2 packages, simply execute this command. And you should see the complete list. However, this list might be long. And let's learn how to search for a particular package. For example, let's try to search for a package that contains the word joined in its name. To do that, we simply execute this command. So again, we use ROS2 package list to list all the packages, then we filter the result with grep, and we search and narrow our search such that we search for all the packages containing the word joined. And if you type this, you should see something like this. And we can see our joint state publisher GUI. Good. The next step is to create the package, URDF, C++, and the launch files. In fact, in this video tutorial, we are not going to explicitly write C++ code. Again, let's practice sourcing the environment. So close this terminal, open a new terminal, and inside of this terminal window, let's again source the environment and create the underlay. Then let's go to the home folder, and in the home folder, let's create the folder called demo_Xacro, and inside of that folder, we will create the source folder. To create these two folders, let's execute this command. The next step is to navigate to the source folder. We do it like this. And in this source folder, which is currently empty, we need to create our empty package, or better to say, to initialize the package structure files and folders. To do that, we need to execute this command. ROS2 package create is the command. Then we need to specify the build type. We are going to use m and c make, and then we give the package name. Over here, I'm going to give the name, which is demo_Xacro, which matches the workspace folder. Okay, this is not a big deal. However, you can also change this name if you want. However, later on, you need to also change this name in all other files. So let's execute this, and let's see what's happened over here. A new folder is being created, and let's navigate to this folder, and let's see what is inside. Let's explain these files and folders. First of all, cmake lists is a configuration file which explains to the build system how to build this package. We will modify this file later on. Include folder can contain additional files and folders, which can be, for example, files that are included or something similar. Package.xml is another configuration file for our package, and the source folder contains the source files. When I say the source files, these are actually the C++ or Python files implementing our nodes. In addition to these files, we are going to create 3 additional folders. These folders are going to be created by running this command. And let's list the new folders. First of all, the configuration folder will be used to store the rviz configuration file. Then, the launch folder will be used to store the Python launch file. The Python launch file will be used to define and to run our nodes simultaneously. Then, the model folder will contain the Xacro implementation files of our model, and that's basically it. Okay, the next step is to create the URDF and Xacro files. Next, let's navigate to the model folder. Obviously, this folder is empty, and in this folder, we will create 2 files. To create these files, I'm going to use Visual Studio Code. I will run Visual Studio Code like this. If you don't have Visual Studio Code on your system, then my suggestion is to install it. I created several video tutorials on how to do that. Just go to the YouTube channel and search VS Studio Code install Linux Ubuntu. Let's create the first file. The name of the file is, let me type it, it's parameters.xacro. Okay, so here's the file. I usually like to name the files which contain the Xacro macro segments by using actually the extension .xacro. Okay, so here's the file. Save it inside of the model folder. And to save time, I'm going to paste the content of the file, and I will explain the meaning and the purpose of all the parameters inside of this file. Namely, let's look into the robot geometry. Okay, so here it is. Here's our robot. The robot will consist of two links. Here is the first red link and the second blue link, and they're connected by the joint whose center is located by this light green, or represented by this light green dot over here. Oops, let me zoom in again. Here it is. And you can see the dimensions of the link. Both links have the same shape and the dimensions. You can see A, B, and C. These are the dimensions in the X, Y, and Z directions. Then you can see the center of the first link represented by this light green circle, and then you can see the displacement of the center of the joint with respect to this coordinate system, which will be located here at the base. Okay, so let's start implementing these parameters. In the URDF, or better to say Xacro files, these parameters are implemented like this. First of all, every Xacro or URDF file has to start with this line. This is the standard line which tells to the system that this is an XML file. Then, this is how we write comments. We start comments like this and we end comment like that. Here I usually like to explain what is this file about. This file is about robot model parameters, and my suggestion to everyone is to add as many as possible comments. Then over here, this is the standard line which defines Xacro address, and let's start with link dimensions. Again, comment, and this is how we parametrize the model geometry. We type Xacro, then property, then we give a name to this parameter. The name of the parameter is A, and we specify the value. It's 0.1. That is A, in my case, is 0.1, and here it is. We do the same thing for B and for C. Here is B, and here is C. In this way, we specify the link dimensions. Then, I need to specify the value of S. That is, I need to tell to the system how far is the center of this link from this base over here, and that's the parameter S. I simply say that S is C over 2, and here you can see the power of Xacro. Namely, you can insert formulas. That is, starting from these parameters, you will later on derive everything. Then I need to specify the value of Q. I do it like this. Here is the value of Q. It's basically the distance of the center of the joint with respect to the base over here, and here it is. Then I need to specify some additional properties that define the dynamics of the system. When I say the dynamics of the system, I actually mean everything that's on the left-hand side of Newton equations. In the case of point masses, that's the mass. However, in the case of rigid bodies, that's the moment of inertia. Consequently, to define the moment of inertia, we need to define the density, volume, and the mass. So here's the material density. These are the standard SI units. That is, the density is kilograms over meter cube. You can see that this is a metal. And then we need to define the mass. The mass is simply the density times the volume. Since we are dealing here with prismatic links, the volume is simply A times B times C, and we simply multiply everything by the density to obtain the mass. Next, we define links' moments of inertia. For those of you who are not mechanical engineers, moments of inertia might be difficult to understand. However, there is equivalence between mass and moments of inertia. In the case of point masses, you're dealing with masses. However, in the case of rigid bodies, you're dealing with moments of inertia. And here are the formulas for the moments of inertia around the X, Y, and Z axis. And these axes are actually located over here at the center of the link. And we need to implement these three formulas. Not a big deal. You can see how they're implemented. Ix, 1 over 12 multiplying mass multiplying b squared plus c squared. And that's exactly the formula given over here. Simple as that. Nothing special. We do the same thing for Iy and Iz. Then, we need to define a macro that defines the inertial section of the robot body or of the link. Namely, in another file, we're going to use this macro over here, and this macro will actually significantly simplify our code and description of the body. So how to define macros? Well, first of all, you need to give the name to a macro. In this case, it's inertia body, and for example, in another file, instead of writing this code segment, I will simply say inertia body, and this segment will be actually added to the code. So let's define inertial element. You start with inertial element, you end with the inertial element, and then you need to define the displacement orientation of the center of the mass frame of the link with respect to the base of the link. And obviously, in our case, if you look at the geometry, the center is located over here, and its distance from the base is s. So let's simply write that x, y, and z, 0, 0, s. S is the displacement in the z direction, and we don't have any rotation of coordinate frames. Consequently, this parameter RPY, which stands for roll, pitch, and yaw, Euler angles, which define rotations, are 0, 0, 0. Then we need to specify the mass value. Again, we use the Xacro value or parameter. Here it is. And then we need to specify the so-called matrix of inertia or tensor of inertia. We need to specify Ix, then Ixy, Ixz, Iyy, Iyz, etc. And that completely defines the moment of inertia. And over here, I need to actually correct something, since there is an error over here. This should be, no, there is no error. Ixx, let me see, Ix, Iyx, Ixz, Iyy, Iyz, so it's perfectly fine. Note over here that you have these products of moments of inertia, Ixy, Ixz, and Iyz. Since the object is completely symmetric, they're all equal to 0. And that's it. That's our macro. Then we need to specify the colors. First of all, again, this is kind of a macro, although not exactly Xacro. This is a pure URDF macro. I specify the blue color, and then I give the RGBA code for that color. R stands for red, G stands for green, and B stands for blue. A is actually the transparency. Since I want to have pure blue color, I have 0 for red, 0 for green, and for blue I have 1, and the transparency is 1, which means that my element is completely non-transparent. And I do the same thing for the red color. I have RGBA code over here. Since I only want to have a pure red color, over here I have 1, and other two values are 0, and that's it. So let's save this file and let's continue. Note over here that we started the robot parameter description with this tag robot, which means that we need to also close this tag over here, and that's it. The next step is to define, or better to say, to create an additional Xacro file that implements the links and the joins. That additional file will actually import this file. So let's create the second file. Click on File, New File, and let's call this file as model.xacro. Be careful over here not to make spelling errors. Save it over here, and let's paste the content of this file. Here it is. Okay, so let's explain the file line by line. Again, since this is an XML file, we need to add this line. Here's the comment that defines what is this file about. And here again we start the robot description. We give the name to our robot. I simply call it a simple robot, and then this part over here is standard. Note over here that when we defined the parameter Xacro file, we didn't give the name. That was not necessary. However, since this file actually completely defines the robot joints and geometry, we need to give the name. And over here we include the file. Namely, inside of this file, we want to include this file with the parameters. To do that, we simply need to use this line. We type Xacro include, then file name, And over here we need to specify the path to this parameters.xacro file. Note over here that the path should be defined relatively to the base folder of our package. So where is the base folder? Well, the base folder is actually this folder over here. And here we can use this trick over here to find the path. So we simply say find the path of our package, and the package name is demo.xacro. And then over here, instead of this line, this complete path will be placed, and that's done automatically. Then our parameters.xacro file is located in the models folder, and here it is. Okay, now we have included this additional file, and here you can see the power of Xacro. You can split your file and implementation in many different files, which can be seen as header files or some implementation files, and then you can simply include them in additional file. This makes your code reproducible, readable, and someone else can use pieces of your code. Okay, this is a disciplined way of implementing robot models. Next, we need to define links and joins. Okay, so what do we need to do? First of all, let's go back to our geometry. Over here, I want to place the world frame. Okay, so I want to place it here at the base. To do that, I need to define a fictitious link called world, and then I need to close that link. And this link will not move, nothing will happen with this link, it will be just fixed to the base, and its name will be world. Later on, once we bring up the RViz model, you will nicely see the world frame. Next, I need to define a fixed frame associated with this link. It's called fixed joint, type is fixed, and I need to define the parent link. The parent link is actually the word link, and the child link is the first link. Note over here that whenever you define joints, you need to specify the parent link and the child link. Here's the child link. And let's go over its description. First of all, you start the link tag and then you end the link tag. Then you define the visual representation by starting and ending this tag, and everything inside defines the visual representation. Okay, so let's see what is this visual representation. It's simply a prismatic element. In URDF and Xacro, we model the prismatic elements as boxes, and then you specify dimensions A, B, and C. Note over here that it's completely parametrized, and these parametrized parameters are defined in this file, and this file is included in this file. So inside of this file, we can refer to A, B, and C. So these are the dimensions. Then we need to define the displacement and orientation of the geometric center of the link with respect to the base. And you can see over here the dimensions are 0, 0, and S. That is, we are placing the center of the link exactly over here. And this S dimension is the translation in the Z direction of the center of the link. And this is how we do it. And over here we specify the material name, it's red. Now, once you type this line over here, basically you're adding this part over here, or actually this part over here. Simple as that. That's the power of parametrizing everything. Then we need to define the collision, which is simply a collision box. This is necessary for control or for move it or for some planning or for some dynamics, such that we can detect collision of links. So here we simply implement the collision block, which is simply a copy and paste of the visual block. Usually that's the case unless you want to have a different collision box. And then over here we need to add the inertia description. To do that, we simply use Xacro inertia body. And here comes the power of Xacro language. Namely, this thing actually means that this whole part over here will be included. That is, the interpreter of this code, instead of this line, will take everything from this block and paste it over here and include it in this file. Okay, that was the first link of the robot. The next step is to define the first joint. The first joint is actually located over here. This is the center of the frame or the origin of the frame of the first joint. So let's see how do we do that. First of all, we give the name to the joint, we specify the type, it's the revolute, this means that this is a rotational joint. Then we need to specify the parent link, it's the first link, the child link is the second link, that is, the child link is the second link over here. And then we need to place the origin or the 0, 0, 0 center of our joint. However, this origin is specified with respect to the previous coordinate system. That is, with respect to the coordinate system called fixed joint. Now, let's see where is this point over here that defines this origin. In the y direction, it's actually b. So distance from here to here in the y direction is b. In the z direction is q. And that's precisely what's written over here, b and q. We don't have the rotation of that coordinate frame. And then we need to specify the axis of rotation. Obviously, this link over here is rotating in this direction. That is, the axis of rotation is the y-axis. And consequently, over here, we specify 0, 1, 0. Then we specify additional parameters for control. First of all, we specify the effort. This is the maximum torque that can be applied to this joint. Then we specify the velocity. This is the max velocity in radians per second. And then we specify the lower and upper rotational limits. Note over here that these limits are in radians. This is minus 90 degrees and this is plus 90 degrees expressed in radians. And then we define the dynamics, dampings, and friction, which are some additional properties of this model. And that's it. That was our joint. Next, let's define the second link. The second link is actually almost the same copy of the first link, only the color is different. So again, it's a box, A, B, and C. Dimensions, material is blue. Blue is defined over here. And over here, the collision block is the same as the visual block. And over here, we simply add the inertia of the body, and that's it. We end the link, and we end robot, and that's it. Let's save this file, and let's continue. Make sure that you save this file and this file over here. Then go back to the terminal, go to the model folder, and make sure that the files are there. Good. Next, let's go one step back. That is, let's go to the base folder of our package and let's go to the launch folder. Inside of this launch folder, we need to create an additional Python file. This file will be used to start all the nodes at the same time. To create that file, go back to the Visual Studio Code, click on File, New File, and call the file as display.launch.py. Make sure that you don't make spelling errors. So it's display.launch.py. Press Enter and then save the file in the launch folder. Here it is, create file. Good. Here to save time, I'm going to simply paste the content of that file. Again, the purpose of this file is to define how the nodes are being executed and to actually execute them with a single Python script. Okay, first of all, we need to import the necessary libraries and packages. Then we need to define our package name. The package name is demo_Xacro, and that's precisely the name of this folder over here. Then we need to define the relative path of the Xacro file with respect to the package path. Our file, that is this file model.xacro, is actually located, let's go back to the terminal, it's located in this folder over here. And we need to specify its a relative path, or better to say the relative path of the file with respect to the package folder. It is inside of the model.xacro. Then we need to specify the relative path of the RViz configuration file, again with respect to the path or to the folder of our package, and here it is. Note over here that we still didn't create the RViz configuration file. We will create it at the first run of our model. Then we need to define this function. The purpose of this function is to define how nodes should be started and to actually start the nodes. First of all, we need to retrieve the absolute model path. To do that, we simply combine or add two paths together. We use this function to retrieve the absolute path of our package. The absolute path of our package is actually this path over here, without launch, of course. And this command will simply return the path. And then we need to get the absolute Xacro model path. We simply join two paths. We join the absolute path of our package with this relative path of our Xacro model, and we do the same thing for the RViz configuration file. We simply join the package path with the RViz relative path. Here, for verification, we print the absolute path of the Xacro model. Then over here, we load the robot description from the Xacro model file. It's being stored in robot_description, and then we define this parameter with the robot Xacro description. Note over here that robot_description is the standard topic that's being used to communicate our model file. And then we need to create several nodes. First of all, we need the robot state publisher node. Here's how we create, or better to how to create a spawner for this node. We need to specify the name of the package, the name of executable, where the output will be, and we need to pass as a parameter our model description. Note over here that there is one very important thing that you need to keep in mind. The robot state publisher node receives the state information. That is, it receives the state information of every joint. In our case, the state is rotation, angle of the joint, rotational velocity of the joint, and the effort. In this video tutorial, we are only changing the rotational angle, and this information is passed to the robot state publisher. The robot state publisher node takes that information and uses the model of our robot to solve the forward kinematics problem. That is, it's going to calculate the complete transformational coordinate system such that we can display this information. That information is passed through the TF topic, and the RViz uses this information to display the model on our screen. However, we also need an additional node, and that node is being used to set the robot angle of rotation by using the graphics user interface, and that's precisely that slider at the beginning of this tutorial. The name of the package is joint state publisher GUI. The executable is the same. The name is joint state publisher GUI, and over here we specify an additional condition that we want to actually run it in the graphics user interface mode. And then we need an additional node. We need the RViz node. This is how we define it. The package is RViz2, executable is RViz2, name is RViz2. Where do we want to put this thing, or where we want to display on the screen? And then we need to specify additional argument, and this additional argument is the absolute path to the RViz configuration file that will be created later on. And finally, we combine everything and we return. We simply specify how everything should be run. We want to run everything in the graphics user interface. That's why we use this line. Then we specify what we need to run. We want to run the robot state publisher node, the joint state publisher GUI node, and the RViz node, and that's it. Let's save this and let's continue. The next step is to modify the configuration files. To do that, let's go to the base folder of our package, and over here we need to modify package.xml and cmakelist.txt. So let's modify these two files. To do that, go back to the Visual Studio Code, click on File, click on Open File, and over here go to the base folder and open package.xml. Over here you can do several modifications. You can specify the version, you can specify the description, you can give your email address, and you can also add a license if you want. To save time, I'm not going to make these changes. Over here I'm going to make only the necessary changes. So go over here after these two lines and you need to add these 4 lines. These 4 lines are actually telling to the ROS2 system that our package depends on additional standard ROS2 packages. These packages are Joint State Publisher GUI, Robot State Publisher, Xacro, and RViz. And these are exactly the packages we used in this launch file. Good. Let's save the package.xml file, and then let's modify the cmakelist.txt file. Click on File, Open File, and let's go to the cmakelist file. Click over here, and after line 12, let's add additional lines. So these lines are given over here. Let me now copy this such that we don't have an issue. And let's make sure that I didn't create any error while copying this. The purpose of these 3 lines is to tell to the CMake build system that we created additional folders and files, and that CMake system should look for files inside of these folders. So we use install and we specify directory, and these are 3 additional directories we created, and we specify where to install them. And that's it. Simple as that. Let's save this and let's continue. Good. Let's go back to the command terminal, go 1 step back, then go to another step back, and go to the demo Xacro workspace folder. Make sure that you're in this folder. The next step is actually to build everything such that we can run our nodes. However, before we do that, let's do additional thing. First of all, let's install ROS2. ROS2 is a very useful tool used for debugging and for making sure that everything is installed properly. Then let's run this command. You can simply ignore any error if you see it. And then let's update everything by running this command. And then let's check that all the dependencies are installed. To do that, simply run this command. And you should see something like this. All required ROS2 installed successfully. Good. Before you proceed to the next step, make sure that you saved all the files. I'm simply going to go to these files and press Ctrl S. And then let's go back to the terminal. We need to build everything. To build everything, again, make sure that you're in this folder, make sure that you sourced everything, and simply run this command. This command will install, or better to say, build everything. You need to type colcon build, then this parameter symlink install, and then you need to specify the packages. You're simply specifying a single package, which is demo Xacro. Press enter, and let's hope that there will be no errors. No errors. Perfect. Let's then open a new terminal and let's run our launch file. Open a new terminal, and over here you need to run this command. This command will actually create an overlay. That is, it's going to run the setup.bash file, and this setup.bash file is not the base setup.bash file, it's actually the setup.bash file inside of our package. So press enter, and then let's finally run our display.launch file. To do that, simply type ROS2 launch, then the name of the package and the name of the executable, which is display.launch.py. Press enter, and let's see what's happening over here before we go to RViz. Here, the most important thing is to search for errors. So let's see. All log files are given here. Fine. Default logging verbosity set to info. Fine. Over here, I'm actually printing the absolute path to the model.xacro file. Namely, if you go back to the launch file, you can see this print statement. And this print statement is exactly this statement over here. Then let's see, are the nodes started with no errors? Robot State Publisher started, Joint State Publisher GUI started, and RViz started. So all the 3 nodes are started with no errors. Let's see. Robot initialized, waiting for the robot description to be published, perfect, centering, so no errors, perfect. So let's go to RViz. Click over here and here. First of all, you will see this thing over here, which is your slider. However, there seems to have to be an issue. We don't see our robot model. Well, this is not an issue since this is the first time we are starting RViz. To show the robot model, click on Add, and then over here, find robot model. Click on OK, then expand here, then under description topic, or over here, make sure that you click here, robot description, and you will see both links. Actually, you see a single link, however, two links are overlapping. That's why you see a single link. And it seems that nothing is being displayed properly. Well, this is because the fixed frame is not being set properly. Click here and click on world, and voila, here you go. Perfect. Let's try to move these robots. To move the robot, you simply need to bring up the join state publisher graphics user interface and try to move the robot. Perfect. Moves like a charm. Okay. Next, let's save this configuration such that the next time we run RViz, we don't need to make these adjustments. To do that, go back to the launch file and see where the file should be saved. It should be saved in the config folder and the name should be config.rviz. So let's just copy the name of the RViz file, then let's go back to our RViz, then click on File, Save Config As, then go to the base workspace folder, go to the source, go here, then click on Config, and over here is a name, save it as config.rviz. Good, perfect. Let's go back to the terminal, press Ctrl C to kill everything, then go back to the original terminal where we build everything, repeat the build command, then go back over here to the RViz terminal, again source the environment, and again launch everything, and let's see what happens. Magic happens, everything is nicely displayed. Okay, that's all for today, and I hope that this video tutorial is extremely useful.